This is, okay, in chapter 4, there's really 2 lessons where we have most of the applications. The one was
No, they can try it.
one section is optimization, the other is related rates. Okay. Yeah, so that's why I said we need to kind of mentally prepare ourselves for this. So we're going to spend today and tomorrow. So we have tomorrow with the bonus period that we'll review. Okay, I just told you that I canceled the quiz, so we don't need to worry about it. And then Wednesday, we'll start reviewing for the test, because this is the last section for chapter 4. Okay, related rates. So related rates has kind of this step-by-step. I know I have this all in a box, but it does help if you get stuck on a problem, if you're working on something from homework, look back at the steps. So the first thing, obviously, you need to understand the problem. And with related rates, we have lots of different variables sometimes that we're working with. So it's good to identify the variable whose rate of change you're finding and the rate of change that you know. So usually what I'll do is I'll read through a problem. We'll draw a picture, which is here, step 2. So draw a picture, label, and then we write down everything that we know and what we're looking for before we even start the problem. Because again, just like optimization, the hardest part was setting it up. Okay, once we had it set up, the calculus is fine. The calculus is kind of the easy part once you get to that. So we want to write an equation relating the variable whose rate of change you seek. Okay. And this is where implicit differentiation comes in. So we're going to differentiate both sides with respect to time. So that's the key. So when we did optimization, we just did the derivative. Remember, we only changed it to one variable. But when we use implicit differentiation, this is when we can't separate the variables.
So
we have
more
more
x and y.
So we might have x and y. We might have x, y, and z. We might have r and we might have theta. We might have multiple variables.
What's the most? What are we going to have?
3. Okay. We do a problem with 3 different variables.
So
3 different things changing. Are we going to what?
Is this multivariable calculus then?
No, that's a little different.
Okay, good.
I mean, okay. We could talk about that. We are dealing with multi variables, and we are differentiating. We're doing the derivative, but that's different. Okay, substitute values back in, interpret the solution. So as I was saying, on the AP exam, we have the free response, and sometimes you have to write and interpret your solution. Okay. Yeah, you want to make sure that your answer makes sense. Okay. So these are all word problems. Don't worry. We'll go through step by step, hopefully. There's only so many different types of related rates problems that we work with in calculus. We work with some volume. We work with some right triangles. Okay, and that's actually the first one that we have. So a hot air balloon is rising straight up from a level field, and it's tracked by a rangefinder that's 500 feet from the liftoff point. Okay, so let me just take that first sentence and let's draw a picture. Okay, we got a hot air balloon. Oh, somebody must have drawn this for me last year.
Why is not as good as you would?
No, I have my notes here, and I did not draw this hot air balloon.
There's no way.
There's no way that's mine. It's not that pretty, but it's not mine.
So you're saying your hot air balloon are prettier? Are you calling that person not mistaken?
I'm not. I guess it is recording.
Wait, did you do your
They're
notes
not-
by hand last semester?
I know, it seems so absurd, right?
Did I what?
Do your notes by hand last semester? Or?
No, I used my old tablet.
Oh.
I'm happy to bring it sometime if you'd like.
What is it? Is it like the one Dr. Mendelsohn used to
Yes.
use?
Okay, so here is my hot air balloon. Oh, it's not that bad. Okay.
That was pretty. Sounded like cool.
Oh, it's a hot air balloon. Oh, I need like the ropes. The ropes come down. Okay. All right, don't look at my picture. I'm not very good at drawing.
Yeah, isn't a rainbow supposed to be rainbow? Could we draw a rainbow?
Do the Darth Vader one like that one at the
Shower.
The balloon.
Okay.
There's a hot air balloon show in New Mexico every year.
Everyone knows
I
about
know,
that.
you say.
Okay, I'm not going to say all, but many of the problems that we solve for with related rates have a right triangle. Not all, we're going to see plenty that don't. But this one is a right triangle. Here's the rangefinder. So here's the hot air balloon that's going straight up from a level field, okay? So this is our right angle. It's going straight up. And they said this is 500 feet here. You know, rangefinder. You know what that is?
Yeah.
Oh, that was the thing I didn't know that something like that existed. So that's the
Yeah.
part of the problem that got me.
Like if you're golfing, anybody
Yeah.
golf, rangefinder?
It's a
Okay.
thing that you point at a thing and it tells you the distance.
I don't have the patience
That's
to
wait,
golf.
that exists, that's so cool.
Okay, so
Yeah, it's a laser.
somebody's standing here with a rangefinder, 500 feet away from the liftoff point. Good so far. That was just the first sentence.
So is that negative 500?
No, it's not 500 feet. So here's the thing. This 500 feet is not changing. Now we're going to have to work with problems where sometimes the balloon is going this way, maybe somebody's walking away from the liftoff point. So we have multiple, remember these are what we call related rates. It's how the rates that change are related. Okay? So at the moment that the rangefinder's elevation is pi over 4. So I'm just going to put in theta here. So when theta is equal to pi over 4, the angle is increasing at the rate of 0.14 radians per minute. Now, that is a rate. So we need to be able to take this rate and write it in notation. So this is the change in the angle, so radians per minute. So I'm going to write this d theta dt. It's the change in the angle, right, with respect to time. So we just said this is 0.4. Yeah, get used to the dt. It's all over this lesson.
Yay.
All over school.
Yeah.
Okay, so this is 0.14 radians per minute. So kind of imagine that the balloon is going up into the air and the angle is increasing at 0.14 radians per minute.
Does it start at pi over 4 so it's 0?
No, okay, so when we're saying at pi over 4, that's the rate of change. At pi over 2, it
Maybe different.
might be different. Or pi over 3, it's going to be different. So the thing with basically with the rates, they're constantly changing at different points. Okay, it's not going to be a constant change. Sometimes it's constant, but this one is going to be changing as the balloon rises. It's the angle's changing. Okay, and the rate of change that the angle's changing is increasing.
I get the gist.
It's a little confusing. Okay, we need some other variables here. So what we want to do is figure out what? We want to figure out how fast is the balloon rising. So we need to pick a variable here. What variable can we use to represent the vertical distance?
H, Y.
You want to use H, we can use Y. Any of these are
Y.
fine. I'm just going to use Y because I had it last year. So I'm going to say we want to find dy dt. Okay, so do we understand the problem? So step 1 was understanding the problem. We're trying to find dy dt.
Why? Isn't that just the height? Oh, okay.
Well, we don't know what the height is. We're going to figure out what the height is. So how could we do that?
Wait, why do we replace that with the...
This is changing, okay? This is why. It's changing. Is the 500 feet
Oh.
changing?
That's like the position.
Okay, so there are two things that are, basically what you have to look at is there's two things changing here. It's rising up in the air, so y is changing and theta is changing. 500 feet is not changing. So we want to look at these three things. Is there an equation that's going to relate all three of those parts? Think sine, cosine, tangent. That's my hint. Which one's gonna make sense here?
Tangent.
Okay,
Cos
opposite,
theta over adjacent.
adjacent. So we wanna write, I'm just writing out steps here so when you guys see these types of problems on the homework. So we wanna write an equation relating the variables. So that's going to be tangent of theta equals y over 500.
And then plug in pi over 4.
Okay, the only thing we don't want to do plug in too soon. We can only plug in what's constant. Since 500 feet is constant, I can plug that in, but I don't plug in pi over 4 until I'm done differentiating. So, So again, so only plug in what's constant, leave all the other variables there. Okay, so we did step 1 and step 2, step 3. Step 4. Step 4 is differentiate both sides of the equation implicitly with respect to time. So we want to take d dt of both sides.
So the 500 is constant.
Yeah, I would just, if it helps, rewrite it as 1 over 500 y, just so you can. Everybody okay so far? Just taking it step by step. So what's the derivative of tangent? Secant squared. So remember, since it's with respect to t, it's going to be secant squared of theta d theta dt. Remember how we have to this is kind of like chain rule in a way? It's like the derivative of the outside, keep the inside the same, times the derivative of the inside. Remember when we did derivatives with respect to y and we had to apply that rule. What about the right side? We just get 1 over 500 dy dt. Now what?
Replace.
Okay, what now is what else can we plug in now?
D theta d.
Right, we know d theta dt, and we know, so now is when we take this information and we substitute that in here. So we don't want to substitute it in too fast, okay? You want to differentiate first, and remember, only plug in what's constant to the equation. Okay, good? Running out of room. Should have made more room here. Okay, so it's 1 over, what, cosine of pi over 4 squared, d theta dt, so 0.14, and then 1 over 500.
Where do we get the cosine from?
Secant squared is 1 over cosine, or secant is 1 over cosine, so
Multiplied by 500.
Oh,
it's
yeah.
going to be cosine of pi over 4, which is root 2 over 2.
Oh, cos theta
Squared.
is.
Remember, this was,
Cos theta is.
I'm running out of
4.
right here.
Wait, where did we get that d theta dt? d dt is secant squared.
What's the derivative of
Oh,
tangent?
right, we're doing the
So
derivative.
it's 2
Got it.
now.
Okay, so this is going to be 2 times 0.14,
So
Oh,
0.28.
0.28. And then we're going to multiply that by 500 to get dy dt.
How's it 2? Just because
1
of
over a half.
students are.
What's cosine of pi over 4 is root 2 over 2.
Oh,
When we
squared.
square it, we get, can you picture it?
Oh, yeah, 2/4.
Do you want me to write it down?
1/2. Yeah, I got it. Hang
You
on.
sure? And then
Yeah.
take the reciprocal, we get
Yeah.
2.
Yeah.
What do we get when we multiply?
But we're multiplying out the.
What's wrong?
I'm just seeing d dt. You multiply the theta to the d, and then on the right one it's dy dt.
Yes.
Yeah.
Because this was theta and this was
Right,
y.
Right, that makes sense.
We should have different
Oh, right,
rates.
those are the-
Remember, the whole section is called related rates because you have different rates that you're
Right.
relating to each other. What do you get for dy?
140.
dy dt, 140. Okay, now the last step. Let's interpret the solution.
Yeah.
Or
that's
just,
good.
what was the question asking?
meters per, no,
How fast
feet
is it going?
per minute.
Okay, so the balloon is rising at, learn to write a
140.
sentence. I know it's not English
120
class.
feet per minute.
Feet per minute.
Oh, okay.
Do we know
That makes more sense.
Okay, look at the units.
what you, oh, this.
Oops. How did that happen?
Jordan, are you okay?
So our answer is the balloon is rising at 140 feet per minute when theta is pi over 4. Okay? It's only when the angle's pi over 4. We talked about at a different angle, the balloon might be rising at a different rate. Okay. Good so far?
If you chose X instead of Y,
It wouldn't make a difference at all.
but you'd have to write like dx dt.
Right, so, okay, here's our next example. Has 3 different variables.
Woo! Should have given us more room. Thank you, Susan.
Oh, you can do it.
Just zoom way in so the
See?
Oh wait, you're like using paper.
Oh, wait.
Don't
Oh,
make me say it,
Jordan.
See?
Just
I want to kill this.
Okay, okay.
Hey, Walker. Say it, please. What?
She's soft.
Really, an
I just-
EMP
I
device,
just-
that's
I'm
the
charging
comeback
myself.
you're gonna go with?
Okay, guys. We're gonna do this example. I'm gonna do this example. You can pay attention, and if you're not paying attention, then you could just be quiet.
Sleep?
Go to sleep.
Okay.
Okay.
Just start.
Okay, a police. Tired. Okay, a police cruiser.
That's a hard one.
It is a hard word.
Is it?
Approaching a right-angled intersection from the north. Okay. From the north. So here, I'm just going to draw kind of an arrow. So here is the police cruiser. It's coming from the north.
Should we
So I'm
draw
going
the
to.
car?
What's that?
Should we draw the car?
You can draw a car. I don't think I'm going
Oh,
to try to
okay.
draw a car here. I'm going to put the police here. Okay. So they are chasing a speeding car that has turned the corner and is now moving straight east. Okay, so imagine the speeding car is going this direction. Here's the intersection. So the speeding car is out here. Okay, so the police is coming down towards the intersection, but they are going east. We're okay with that? So when the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car, so that's actually the hypotenuse, so this distance is increasing at 20 miles per hour. So if the police are moving at 60 miles per hour at the instant of measurement, how fast is the car moving? Okay.
Whoa, that's
The
a lot of
speeding
questions.
car?
So we're gonna figure out how
Yes.
fast the speeding car is
It
going.
gives you the cruiser speed.
So first thing we're gonna make,
Police be sitting there like doing
No,
they're going 60 miles per hour.
I have something
They're
to do the math
chasing.
for them.
We're doing the math for them.
I don't know.
Do they have like people they can call to do the calculus?
You. Okay.
Yeah, right.
Should I do this?
I don't think I have a police scanner.
Jordan, I did calculus master.
Now here's the situation with this problem is nothing is constant. Everything is changing. In the last problem, the rangefinder was 500 feet away. But now, all 3 things. The police are moving, the speeding car is moving, and this distance, the hypotenuse, is changing.
Because the speeding car's going fast.
So I'm gonna just put in variables for right now. Okay, we'll use this as X, this is Y, and we'll make this Z. If you wanna use A, B, and C, that's fine. But we're gonna relate these. We don't have an angle this time. We just have 3 measures. How do 3 measures relate in a triangle? Pythagorean theorem. What were you gonna ask?
I was gonna ask, like, don't we know X and Y?
they're changing. So I'm not going to write those values in just yet because they are all changing here. Does that make sense? In the last one I labeled 500 because, so remember in the last example here, if you actually look at how I labeled my picture, I put theta. I didn't put pi over 4. I put y because that distance is changing. The only number I actually labeled in my picture was the constant. So I want you to try to get into the habit of not labeling too much, just labeling what you know in terms of the variable. Oh, they're practicing their spelling words. Okay. And okay, so we know the variables, but we don't have anything constant here. So what do we know? Or what do we want to find? We want to find the speed of the car. So that's going to be, what's that? We don't need to worry about the angle this time. We just have x squared plus y squared equals z squared. So this isn't going to use sine, cosine, or tangent this time.
How is labeling that too much information?
Because it's changing. Okay, let's see what we know. We know what? We know,
20 miles per hour.
okay, so when the police, so when y is equal to 0.6 and x is equal to 0.8, what else? So what do we know at that instant? We know that,
Z is equal to.
okay, so we know dz dt is 20, and we know dy dt equals 60. And actually, I'm going to make this negative 60. Okay, I'm just writing down in words. Miles per hour, that's a rate. So this distance is increasing at dz dt is 20 miles per hour. Dy dt. Now why did I label that negative 60? Because it's going down. The distance is decreasing, right? As it gets closer to the intersection, it's getting closer and closer. The distance isn't getting greater. It's getting smaller. What about dx dt? Should that end up being positive or negative? It's positive. It's going away from the intersection. So we want to find dx dt. The speed of the car. Dx dt, that represents the change in x with respect to time. Okay? So that's why it's helpful to just label your picture. I didn't label the 0.6 and 0.8. If you want to, it's fine. I mean, it's whatever you want to write down there. What's going to be the equation relating these three? We said it was going to be x squared plus y squared equals z squared. Now we don't plug anything in, nothing is constant, so we're going to differentiate right away.
Oh, good call.
So d dt of both sides. Sorry, I didn't leave a lot of room, but we get what? 2x. Don't forget the dx dt. Before, when we did implicit differentiation, we didn't have to worry about it, but because this variable on the bottom is different, we do. Plus what? 2y dy dt. And then it has to equal 2z dz dt. Natalie.
If we didn't have to do the dy dt part, we have two lines dy dt anyways, just by doing
Mm-hmm.
just by doing the change word, right? So how come we don't have dy dt squared? Because you have dy dt times dy. Because if we were just do the derivative, we have without worrying about adding, like when we do the
You have just 2y.
wouldn't we have to also do dy dt?
Only when you do implicit differentiation.
Okay.
If you're,
Okay, I sort of see what you're saying. Because before, how come we didn't have to deal with the x again before?
because it was d dx, so both sides.
Okay.
That's why.
Yeah.
Okay, what can we do now? We can start plugging in stuff?
I was, yeah.
You guys are so, all right. Oh, one thing we didn't do yet. So when y equals 6 and x equals, or 0.6 and x equals 0.8, we could figure out here z equals 1. It's a 6, 8, 10. You want to write 1.0, whatever. It's a 3, 4, 5, 6, 8, 10, basically. Use Pythagorean theorem. So we could figure out at that instant. So when y is 0.6, x is 0.8, z has to be 1. Because we need to have that to plug in. Basically, once you start plugging everything in, you should only have one unknown. You don't want to have 2 unknown variables. Do we have enough information? We can cancel out all the 2's if you want. Does that make it easier?
A little bit.
Okay, so let's plug everything in. So it's 0.8. Oh no, yeah. Yeah, x dx dt, so that's what we're trying to find. Plus y was 0.6. dy dt is negative 60. And z is 1. And dz dt is 20. So it's not that bad. Just multiply it out so you get 20. 0.6 times minus 60, yeah. So negative 36. So then add it, and then divide by 0.8. What do we get? Hopefully it's something.
175. 20.
How about 70?
70.
Plus 1. No.
Remember that one where we make sure our answer makes sense? Hopefully they're not going 175.
70. Well, it could be.
No,
They didn't
it
say
makes
what kind
sense
of car
if
they're
the
driving.
speeding car was, but a police car actually, a minivan is faster than a police car. That's why they're getting new cars. Yeah, a minivan's faster than Crown Victoria in a drag race.
Oh, no one's drag racing in a minivan.
I'm glad you know that.
If you ever need to make a quick getaway, Jordan. When?
Okay. We're good?
Can you stop here?
No?
Well, we have to. Good time. Your screen cap looks like it's running out of room.
Oh, yeah.
Yeah.
How long do you have left?
Oh no.
I
Has
think
been
we need to
increasing.
stop here.
We can do this one.
No, no.
Just do it, just do it.
Please.
Of course we do
This
it.
one looks like fun, so I think we should wait for Jackie.
They're all fun.
They are all
This one
fun,
looks
so
especially
Jackie
fun.
should be able to
There's
experience
a tank.
And it's the conical shape.
It's a conical tank. What's a conical tank? I always run
Shaped
into
like a
this.
cone.
Shaped
It's
like
a
a
giant
cone.
snow cone.
And it says, it stands point down. So it looks like this.
Oh, you just
I
tricked
have
us into
no
thinking
idea
it
what
would-
would be inside the conical thing.
And and it's like this, and it's,
What's in the tank?
I don't know. Water.
Yeah, but like are there fish in the water?
What's that?
Are there fish in the water?
Ooh, good question.
I'm gonna make fish in
It's 9, so let's see. So water is going,
That's a nice picture.
water is going in. Well, I can do 3-dimensional shapes. Remember geometry? I cannot make other things. I could do
My
cones,
cars are really cute. I have
cylinders.
a police car and
I don't make cars, no.
Is that like a requirement when you're being a math
I don't know, I feel like
teacher?
some should be sketchy, so maybe.
Good question. I don't know. I'll have to survey the other teachers.
Watch them all be able to go.
Okay, so water runs into a conical tank at the rate of 9 cubic feet per minute. That is volume. That is right here. That is dV dt.
Are we required to draw cones?
That's volume. dV dt.
Cute. Yeah, I think you realize that.
Oh yeah, and I forgot to put that in my unit.
I'm making fish in my cone.
So basically, if you saw area, you would say dA dt. Other measurements, like we've only done linear measurements so far, or angle. Okay, the tank stands point down and has a height of 10 feet and a base radius of 5.
Does it matter that it stands point down?
Those are constants.
So these, okay, be careful though. Okay, this is and the radius is 5. Now the radius is, now you're right, the radius is 5. However, that's the tank. The water that's filling up inside the tank is not staying constant.
Why?
So the relationship So when h equals 10, r equals 5. So the radius is always going to be half of the height.
Can you explain that one more time?
Oh, the
'Kay,
radius.
do you want me to
of the
write it out?
water Or the radius of the cone in general.
Here, let me write this out. What's the ratio of r to h? 5 to 10. Basically, you could make, imagine here, like there's the height. You have similar triangles. So at every point, at any point in the tank, the ratio of the radius to the height is going to be 1 to 2. They're both changing now.
They are changing, or what did they say, or why are they
They're
constant?
as the tank, so imagine you have a tank that's not changing, but the water level is changing and the radius at which it's reaching is also changing.
Oh, like in the tank is half
So
full.
it's like the top
Oh.
level of the water, that's where the radius is.
So it's,
I would like to call them.
so I can't say, so what if the water level is right here? Is the radius 5?
So
No.
if that was 6, the radius would be 3.
Exactly. So if this is reaching to a height of 6, then the radius is going to be 3. So knowing this, I can figure out r is equal to 1/2 h. Now my volume. Actually, what are we trying to find? We're trying to find dH dt, right? When h equals 6. Does that make sense? So we're trying to, notice here they didn't give us a dr dt because the rate at which the radius is changing.
How do we know that H is 6?
It says, sorry, I didn't read the rest of it. How fast is the water level rising when it's 6 feet deep?
So you do like 6 over 10 equals x over 5.
But
So it's R is equal to 3.
okay, but that's true at that specific point, but remember it's changing. So let me write this out. What is volume for a cone? Anybody remember? You have to know these things.
Like,
Oh, it's
no.
It's
The area of the
area of the base, pi r squared,
Pi
squared height.
times the height.
Minus
How about divided by 3 or
Yes.
1/3? You're like, yes, what?
That's not what I was gonna say.
1/3 pi r squared times the height.
Why do we divide by 3?
So for cones and for pyramids, they're 1/3 of their corresponding volume of a cylinder. So like, for example, if you took a cylinder of the same radius and same height, you would be able to fill that up 3 times with a cone. And same for a pyramid. If you took a pyramid and took that base and the same height, you could fill up the pyramid 3 times into the prism. That was something you should have learned back in geometry, but
Well,
I would
Thanks,
teach
Patty.
it was a long time ago.
I don't know.
Our geometry teacher was really into like teaching.
Oh, I'm sorry.
No. We were also in 8th grade and had a major case of senioritis.
Hey, that's not a thing.
Yeah, is it?
Yeah, it's really not.
Not a thing.
I didn't do any work that
Okay.
year.
So actually this one's a lot, the setup for this one was more difficult, but when we actually go to solve it, it's the easiest one. Because when we plug h over 2 in, now do you see why I needed to figure out what r was equal to in terms of the height? Remember with optimization we needed to eliminate a variable, we needed to do the same in this case. What do we end up with? Well, let's see, this will be 4 on the bottom, so I'll get basically pi over 12 as, if you want to think of that as my coefficient, and then h to the 3rd. Are we okay with that, just simplifying? And now when we do the derivative, so we want to do d dt at both sides.
Oh, you just evaluate the right side.
Yeah. Oops. Yeah, what is that going to be? So dv dt is, well, this is just the coefficient, so that just becomes pi over 4.
Yeah.
Okay. H squared. dH dt. And now we plug in what we know. What do we know? And we did say dV dt has to be positive, right? Because it's pouring into the tank. Just be careful if it says it's draining from the tank. Let's say there's a hole in the tank or a leak, then you would